Hello students, a very warm welcome to the 50th fortnightly workshop. I hope every one of you is doing super great. So today we have an exciting topic lined up for you. This is evolution and importance of SI units in metrology. We will discuss the evolution, legal framework, awareness, its significance, and much more. This workshop is now available to students who are studying in 6th to 12th grades. I'm Richa Bhambi, your moderator, and I'm thrilled to be part of today's session. I would want to thank everyone who has joined us for today's session. Your presence contributes immensely to the value of this gathering. Let me begin by introducing our platform, CAN, which stands for the Knowledge Awareness Mapping Platform, aimed at bridging the gap between schools and scientific community. This ecosystem is essential for nourishing a love towards science, technology, mathematics at camp. We also offer a wide range of activities and programs, including coding, AI, robotics, scientific tours, and events. Not just this, we also have our very famous, the popular teacher training program, which is continuous professional development, CPD. We strongly believe that education is more than just learning subjects. It's also about applying knowledge, addressing real world problems, and planning. Our goal with is to create a learning environment that unites educators, principals, students, and the community at large while strengthening the idea of learning beyond textbook. So as we move forward with today's workshop on SI units and metrology, remember that you all are members of a large community that values knowledge, innovation, and growth. Moreover, you all are considered a group of young leaders who will shape country's fate. And to embark you in this journey, CAMP is here to support you through workshops like these. May I now take this opportunity to kindly introduce and welcome our guest speaker for today's session, Dr. Poonam Arora. Dr. Poonam Arora is the senior principal scientist and head of Indian Standard Time Division in CSIR NPL, professor in Academy of Scientific and Innovative Research, secretary of the Indian Women Scientists Association, the Delhi branch. We encourage active participation throughout the session. So students, please feel free to share your ideas, questions to Dr. Poonam Arora. Over to you, ma'am.
Thank you very much, Richa. Hello, all the students and all the audience present here. I hope I'm audible and my slides are visible to you. Am I? Richa,
Yes,
can you confirm
yes,
if I'm audible and my slides are visible in the full screen mode? Okay. Thank you so much. Thank you so much. So let's get going. So I welcome all the students and all the audience. Thank you very much for being here in large numbers. And this is the summer vacation time, and I hope you will enjoy going through this lecture workshop. So as Richa has already informed you, and you know the topic for today, so I will be speaking on evolution and importance of SI units in metrology, which is basically essential for ensuring precision, thus ensuring quality of life, thus ensuring economic development. So it's all related, and you will get to know this while I go through the slides and during my presentation. So you all are free to ask me questions even in between, but I would probably encourage you can note down your questions and comments, and at the end of the talk we can take your questions one by one. But if you feel impatient and feel like asking, then you can interrupt me in between as well. So I am associated with 3 organizations. You can see a lot of logos on this first slide. So let me explain those before I get going with the lecture. So here in the middle, you see, let me switch the pointer. Yeah. So here in the middle, you see the 7 base units of the SI system, and I'll introduce you to these. Of course, I belong to CSIR, so the logo of CSIR, and National Physical Laboratory, where I'm a scientist, so that's my workplace, my karma bhumi. I'm also a professor in Academy of Scientific and Innovative Research. So when you grow up and you want to take up research and want to do a PhD, or if you want to do internship during your undergraduation and post-graduation, you're most welcome to come to any of the CSI labs. And specifically, if you get interested in metrology, you can come to NPL, you can do internship, you can also get a PhD degree if you enroll in ACSIR. The other organization is Indian Women Scientists Organization, which I'm a life member of, and I'm currently also the office bearer of the Delhi branch. Namely, I'm secretary of the Indian Women Scientists Association of Delhi branch. So with this, and then CAMP platform has provided us this opportunity. The SI units logo that you see on top is what we are going to speak on. And the metrology, the measurement, is essential in any skill that you take. So as a skill development initiative also, this is a very important part of education and awareness activity that we take on for outreach. So before I begin with the lecture on SI system, I would take just a minute to explain about Indian Women Scientists Association to you all, because that is also the co-organizer of this talk and given me this platform. So this organization is a non-profit, non-political charitable organization, and was established way back in 1973. It is having headquarters in Navi Mumbai and already 11 branches spread across the length and breadth of India. We have about 2,000 life members, and this membership is open to all women with a background in science and technology. So as you can see, we have already completed 50 years, and this is the scientific brochure which was brought out to commemorate the 50 years of Indian Women Scientists Association. So what are the activities? What are the objectives? So the objectives, major objective, because it's a scientific organization, is to take science to masses, to develop scientific temperament in the society, promote scientific accomplishments among women scientists, understand problems that women are facing, provide them a platform for empowerment, and also be a representative body of women in science and technology. And we take care of various activities, but namely two major activities are scientific programs and community programs. So you have a lot to gain. You can be part of a science nurture program, popular science lectures you can attend, even some workshops, projects you can do. There are various green initiatives IRSA have started, like awareness about solar energy, biofuels, etc. Community help, I think that's a major objective of any such organization. There's a working women hostel in Mumbai, there's a daycare facility for working women, nursery school, healthcare centers, library, and so on. And for details, I mean, I cannot say it all in this lecture. You please visit the IRSA website and get to know how you can either get benefited, or you can pass on information to others who are needing some help, especially for women in science. But it is not mandatory that you have to be a woman to be a membership. You can be an associate member if you have interest in sciences, and you can also be called friends of IRSA for that matter. So the next organization, the CSIR National Physical Laboratory. So this is the National Metrology Institute of India. So it was established way back in 1947, and it is custodian of national measurement standards through an act of parliament. And the major mandate is to provide traceability to SI units in India. So we have a special position, and we have been given this mandate by an act of parliament. And so if it is so given the duty by parliament, we also feature in the Gazette of India. So there were legal metrology rules which were published in 2011, and you can read this part here, the work related to the realization, establishment, custody, maintenance, and so on, and updating of national standards of weights and measures shall, on the commencement of these rules, be the responsibility of National Physical Laboratory. So you know we have a very important responsibility, and we are the only one in the country, and every country has a one standard National Metrology Institute, and that is the work that we are doing for the country. And for more details, you are requested to go through and browse our link, nplindia.org, where you'll get to know what we do, what we deal with, and so on. So next, now that we say that it's a National Metrology Institute, so what is metrology? So metrology comes from the Greek words metron and logos, which essentially translates to study or science of measurements. It covers all aspects of measurements and determination of levels of uncertainty, because no measurement is perfect. There is always some scope for error or uncertainty. And this is a basic requirement. I mean, we use metrology in everyday life. I mean, everybody does, but especially for all the fields of science and technology, and especially in engineering and manufacturing, this is essential to follow the metrological principles. If you want to have a good business, if you want to do import export, you have to know the metrology and you have to do your measurements correct. So metrology is broadly divided into three fields: scientific or fundamental metrology, which is basically we do for maintaining country standards, for providing traceability to SI units to the end users. Applied and industrial metrology, this is basically pertains to the manufacturing sector for industry. I mean, for making quality products available to the customers, applied or industrial metrology is a must, and it's a key factor for growth. And the legal metrology, so we maintain standards, but who will ensure that a kilogram is kilogram, no one is making a mistake, a liter is a liter? Who will do that? So the enforcement agency is the legal metrology. So there's a department of legal metrology. So all these three aspects clubbed together ensures that we have metrology in every word and spirit of our everyday activity, and we provide quality of life and quality infrastructures to the citizens of this country. So metrology, it is such an important field that an entire day is dedicated to the celebration of metrology, and it's called World Metrology Day. It's celebrated each year on 20th of May to commemorate signing of Meter Convention in 1875. Meter Convention was basically a treaty which has a consensus for worldwide uniform measurements. So, and this is also a reason why we are, giving this lecture today, because we just celebrated World Metrology Day on 20th May, and 10 days later, I'm here to tell you about it. And that is also one of our mandates, to make people aware about metrology and its aspects. And this year is also special because the World Metrology Day is also officially recognized for the first time by UNESCO. So UNESCO is a UN body, UN Education, Scientific and Cultural Organization, which has a set number of days, some international days, which it celebrates, and they are for specific purpose, for creating awareness among people. So marking this day, World Metrology Day, as UNESCO International Day, opens avenues to promote metrology, and which is aligned with UNESCO's mission to construct better world through science and education. So now that UNESCO has taken up, and in any case, World Metrology Day is celebrated with a release of a theme poster and the theme for the year. So this year's theme, because United Nations also deals with sustainable development goals, which many of you must be studying in schools these days. So the topic for this year is sustainability, which is important because data-driven decision making and policy development is essential for sustainability. By making accurate measurements of various aspects like pollution levels, the gas emissions, the chemicals in food, and so on. I mean, it's very important for people to be aware and to provide accurate measurements from the scientific organizations to the government and industries, so that we can make informed choices which contribute to a sustainable future. So why do we measure? Why it's important to measure? So some of the learned scientists, a great scientist, which many of you must have already heard about, said some great things about measurement. So what are these? So Lord Kelvin had said, when you can measure what you are speaking about and express it in numbers, you know something about it. If you don't measure, you don't know it. Then Max Planck, another revered scientist, he had said an experiment is a question which science poses to nature, and measurement is the recording of nature's answer. Another famous scientist, James Harrington, quoted, measurement is the first step that leads to control and eventually to improvement. If you can't measure, you don't understand it. If you don't understand, you can't control. If you can't control, you can't improve it. So measurement is essential. So is it essential just because the learned scientist said so? No. It's important because it hits us all in our everyday life. Metrology is an integral part right from birth, and even before birth. You might have seen your parents going to doctor when the baby is about to be born, and when the baby is born, the first thing what is done is measuring the weight of the baby, the circumference of its head, so to ensure that the baby is born healthy or does it need some treatment, ensuring safe baby food so that everything is in prescribed quantity in baby food, best regulation practices, so that you get the fuel. If you want 10 liter, you get 10 liter, not less, not more. For safe traveling, so when you travel, so the tire pressure has to be in certain prescribed limit. In aeroplanes, there has to be oxygen pressure in the cabin, which has to be prescribed limit. When it goes beyond that level, the oxygen mask fell off. If the measurement is not perfect, you will not get the oxygen mask when you need it. And then for climate change, for measurement, like these days people are talking about heat in Delhi and heat wave across India. So if you can't measure precisely the temperature, how would you know if the climate is actually changing or not? For science and innovation in every field, measurement, that is the way you can make sure if you are improving, if you have made your measurement more precise. For globalization, for doing imports and exports, metrology is the key. If you make a product but it doesn't fit at other place in another country, nobody will buy it. For manufacturing, for ensuring that the quality of products, so that every product behaves similarly and gives the similar result, it's important that there are some scientific metrological measurements done on each product. For healthcare, for safe food, for medicine, for technical forensic evidence, if you can't measure how much is the urea in your blood, or how much is the hemoglobin in your blood accurately, you can either be overprescribed or underprescribed by the doctor. So for the safe treatment also, it is essential. So you see, almost in each part, knowingly or unknowingly, metrology itself. So the first thing probably you do in the morning, or your parents get a liter or 2 liter of milk from the dairy or from the grocery store, or buying 1 kilogram of potatoes, or 1 kilogram of fruit or something. So the measures and measurements are part of our everyday life, and if they are done perfectly, you will reduce your day-to-day stress and thus improve the quality of life. So we have now ascertained the need for metrology. Let's have some quick examples. So metrology, basically, it emerged for economic reasons because of the fairness of transactions, so that what you are paying for is actually what you get. If that doesn't happen, that means you need to improve your metrology. So some example. So Mr. A buys a kilogram of vegetable every week, which can be found all year round. And then the vendor has the balance, which is not properly calibrated. So it's not measuring 1 kilogram as 1 kilogram, but it measures 50 grams less. So it doesn't seem significant for one transaction for 1 kilogram of vegetable that Mr. A buys. But if he buys from the same vendor for one complete year, after 52 weeks, Mr. A will be losing 2.6 kilogram of vegetables. So, so the customer is at the loss. Another example, Mr. B refuels his car, a small car, with 50 liters of petrol every 2 weeks. However, the petrol pump is not calibrated well, and it distributes 2 centiliter more in each transaction. So a quick calculation we can do, back of the envelope calculation. So the gas pump operator is losing 100 centiliter of petrol for one transaction. So for year, he will be losing 26 liter of petrol. And if we calculate 26 liter of petrol in Indian rupees, so the customer is gaining 2,500 rupees and the distributor is losing. So if the metrology is not correct, this is what happens. There will be dissatisfaction either at the customer end or at the distributor end. Now, these are some gross examples. Think of precious metal business. When you go and buy, your parents, they buy gold or silver or platinum. So these are very expensive metals, and even to a milligram, you can lose a large amount of money. For clinical diagnostics, as I just said in the earlier slide, if the measurements are not done perfectly, you can be overtreated for a disease, or your disease can go completely untreated because it was not diagnosed properly. Pharmaceuticals, if you see at the back envelope of the medicine that you are eating, so the composition of the medicine says a microgram of this chemical, a milligrams of this chemical. So if those small measures are not measured correctly, so either you will be getting a side effect of the medicine, which has a certain extra quantity of a chemical, or the medicine won't work. Then another example is precise navigation and timing. All of you must be using Google Maps these days, right, for navigation. When you hire Ola, Uber or something, so how it is done? The navigation is done by the satellites. So GPS satellites are there, and these satellites have atomic clocks on board, and these are synchronized to within few nanoseconds. So all the clocks. So if they are not synchronized, you will not reach your destination, but may end up reaching kilometers apart. So similarly, for strategic sectors like ISRO launching satellites, for DRDO launching missiles, so a small timing error can lead to large errors in the distance. So the target destination will not be achieved. So similarly, there are lots and lots of examples to emphasize on the need of accurate and precise metrology. So what do we do in a measurement? So we measure the numerical quantity or value of a unit. And then there is a unit. So we are measuring 1 kilogram. So one is the numerical value and the kilogram. But whenever we measure, do we measure just one number and we just add a unit to it? No, because no measurement is perfect. Errors are bound to happen. There are errors like our reaction time. When you are reading certain, a balance or something, there is certain reaction time. So this is like one example of an error, but there are n number of errors which can happen. So these have to be accounted for, and these errors lead to uncertainty in measurement. So when you measure a value, you never measure a exact value, you measure it within a range. So the uncertainty is basically the range within which you can make an error. And how you can reduce this uncertainty is by making the multiple measurements. So repeatability, reproducibility, all these are related to measurements. And what is calibration is basically the art of metrology. So comparisons can be used to calibrate and to ensure that the values returned to us correlate with the values based on those of standards. So that's what we do at NPL. We realize the standard of a unit, and then we provide the calibration and testing services to the customers. So the customer can come to us. For example, let's take the example of a kilogram or a meter with their standard weight or their meter bar, and then say, please let me know if my weight is exactly 1 kilogram. So we have a standard, we measure that standard against we measure the device or the artifact that the customer brings against our standard, and we tell the customer how far it is from the exact value, and we tell it with some uncertainty. And to make sure that we reduce the uncertainty, we do repeatable measurements. So why repeatable measurements are important? To know how accurate and how precise your measurements are. So in this view graph, you can see, so if you are measuring a certain quantity, and the innermost red circle is basically the true value or the expected value, and you are making multiple measurements and they are hitting all over. The black dots are the measurements. So they are not hitting right at the center, the bullseye. So this kind of measurement is called low accuracy and low precision measurement. Another set of example, a person is measuring, so he is making multiple measurements and all of them are very closely spaced, but however, they are far off from the true value. So this is a low accuracy, high precision measurement. Another example, their measurements are very close to the real value, but none of them correlate very well with each other. So this is high accuracy, low precision measurement. And then there is this set which is rightly hitting at the bullseye, highly accurate and highly precise measurement. So you measure accurately and you measure the same again and again, and then when this happens, then your instrument is perfectly calibrated. So what is accuracy? It refers to the closeness of measured value to a standard or known value, and precision refers to the closeness. So ideally you need both accuracy and precision, and this you can improve by making multiple measurements. So it is very important, not just in scientific field, but even for you. When you are measuring anything at home, if you are doing it again and again, you will ultimately reduce the errors and uncertainty. So if you are getting bored of too much of metrology concepts and new words and vocabulary, let's go to history. So way back in history, so how the measurement started? Is it a very new field? Is it a very modern field of science as it seems so? No, it's a very old science. In fact, it comes from the ancient times. Even the Egyptians, they were very smart people. So they have pyramids in Egypt, and the brick size of all the pyramids is exactly identical. So they must be doing something very nice to make sure that all the measurements are accurate and precise. So initially, in earlier times, it was not required. Everybody was on their own. There was a lot of spaces. People were making their things on their own. So if I needed a nail, I'll say, to my family, okay, give me a nail of the size of my thumb. So they would know, okay, probably this much. So they'll bring it to me. And my work will be served. But nowadays, when we are working on different parts of major project, and there's a need for standardization of measurement. So now, you have to define what size of nail that you want. You can't just have a random, number related to some size of somebody's thumb. So, and then there was the funny aspect, the birth of imperial system. So probably many of you know about this imperial system, which is in place, which was in place in UK and still in place in US. So that time they said, okay, so how do we make a uniform measure? So they started saying, okay, let's take the thumb of a popular guy, a king, of course, the readily available person and respected, and call it an inch. So the inch was the width of the thumb. The foot was the size of king's foot. And now if the kings change, you know that your foot size is changing, right? And then it eventually became 12 inches. A yard was the distance from the tip of man's nose to the end of outstretched arm. Eventually, later on, 3 feet became a yard. I mean, this system also evolved. But this is how funny as it can be. I mean, how the measurement started. So the British Empire used this method, and then they constantly kept on improving, and the system was in place for a very long time. And similarly, other countries were also adopting some kind of method, similar or a little different. So then there was a need. Then there was a need for the uniform measurements. So in 1586, Flemish mathematician, he said, it's very difficult, the inch, yard, and so on. So why don't we develop a system where we can, convert from one quantity to another by a uniform figure, like the powers of 10. We can multiply or divide by 10 and we get it. So that is called the metric system. And the France was the first country to adopt it in 1795. So after French Revolution, scientists were asked to make a uniform system. By the time it was realized that we cannot rely on nature, or we cannot rely on, kings or persons. We have to have measurements which are based on nature. So then the scientists so this was first example when meter was developed by measuring 1/10 millionth of the quadrant of Earth's circumference running from the North Pole to the equator through Paris. So this was indeed a very nice beginning of making the scientific measurements, not measurements dependent on persons. So then based on metric system, this was evolved, and then the system, international system of units, which is called SI, was developed and announced by France and leading to meter convention. So again, we have come to the same term, meter convention. So I'm going to explain that in few slides. So meter convention again is that treaty where the whole world basically came together, and diplomatic treaty means the governments coming together. So when on the international level, first the governments have to decide, and then the scientists propose what exactly is to be done. So the meter convention was such diplomatic treaty where number of countries signed and agreed that we'll have a uniform system of measurement in place. Then the system was presented in 1960, by General Conference on Weights and Measures. So this is the highest body, which it's kind of a conference which meets every 4 years and decides on all aspects related to SI and metrology. So then the system was adopted. So by 1970s, most of the world switched to SI as the uniform system of measurements. So just a quick comparison to give you a flavor of like imperial and metric system, since we talked about it. So a length, mass, capacity in metric system and an imperial system. So what are the different units and what are their conversions? So 1 inch to centimeter, 1 foot to centimeter. So these kind of strange conversions, and there's no uniform formula. Similarly for mass and capacity. So here you see in United States, because they are still for their day-to-day life sticking to the imperial system, and you see the conversion. So inches to a foot, feet to a yard, yard to a mile, ounces to a pound. So they are all different numericals. So you have to remember all of it, and then Fahrenheit to Celsius scale. But if you see the rest of the world, which adopted the SI system based on metric system, basically, so their millimeter to meter, meter to kilometer, grams to kilogram, all is related by factors of 10. And similarly, in the United States, they also follow a calendar convention, which is a bit different, month, day, and year they write. But in all other parts of the world, including us in India, we go by day, month, and year. But I mean, this is not as critical as the units and their conversions. So for the conversion sake, also now you realize that metric system is much better and convenient. So the SI system, so the prime objective of having the SI system was to have a system which is available for all times and for all people. So everybody should be able to understand it. Everybody should be able to use it for conversions and communication of their results. So the system was adopted, and this had 7 base units. And of course, there was convenience of multiples and fractions of 10. So it's the most widely used system of measurements in place currently, with USA being the only industrialized nation which doesn't use it for their commercial activity. Although for all their scientific purposes, they use it. And apart from USA, there are Myanmar and one more country, Liberia. They are still using for their day-to-day applications, commercial activity in their country. They still use the imperial system, but the rest of the world has completely switched to SI system, and basically all the scientific measurements are definitely done in SI system. So these are the SI units. The SI units, the International System of Units, and it's basically come from French. Why it's called SI? Because the French acronym is Système International des Units. So that's how SI. So BIPM website, so International Bureau of Weights and Measures, says this about the SI system. The SI is a consistent system of units for use in all aspects of life, including international trade, manufacturing, security, health and safety, protection of environment, and in basic sciences that underpins all of this. So that's how it has become very popular, and it is ensured that it is continuously revived, it's continuously evolved. With the measurements improving, with science and technology improving, it is being improved. So now we had talked about the meter convention a couple of times. I mean, I told you that I'll come to it later on. So this was a diplomatic treaty. It was signed in way back in 1875, and it's on that day. So 20th May 1875 was the date when the meter convention was signed. And as I said, it was a diplomatic treaty between nations, and that time it was only 17 nations which signed, and later on more members joined. I mean, as they agreed to this concept. And as a result of this treaty, there were three organizations which were created. So one of them was International Bureau of Weights and Measures, the other was the General Conference on Weights and Measures, and one was the International Committee on Weights and Measures. So BIPM, I'll come to it in the next slide. So CIPM has set up consultative committees for all the units. So they discuss about how a unit is being measured. Are there some reports where we see that the measurements have improved, or the method of measurement needs to be changed, or the definition of a certain unit needs to be changed? So that is discussed, and they meet every year. And in CIPM, there are, to this meter convention, now we have 62 members and 40 associates, but only 18 representative out of these 62 member states, they become part of the CIPM, only 18 members. And we are proud that at this moment, the director of NPL, Professor Venu Gopalachanta, is one of these 18 members of the CIPM, which is a very proud moment for us. And then there was a CIPM MRA, so Mutual Recognition Agreement, which was signed. So this says if a certain thing is measured in NMI of India at NPL, it will also be accepted at the NMI of America, let's say NIST. So this is a degree of equivalence. So measured once, accepted everywhere, because all of these NMIs are following the set standards and procedures, and their activities are peer reviewed. I mean, there are tests, checks and balances applied that we are making measurement as Americans are also making. And then there is CGPM. This is a conference which takes up and discusses the major issues and decides what is to be done for certain units. So this meets every 4 years. So these are all generated. So this was the consequence of the meter convention. So BIPM, International Bureau of Weights and Measures, this is an intergovernment organization. This was established as a result of the meter convention, as I just explained. And this is the International Authority on Standards and Metrology. So it has headquarters in Paris, and it is funded by the supporting governments, the member governments. And its mandate is to provide basis for single coherent system of measurements throughout the world, traceable to the International System of Units, which is SI. And this task takes from many forms, from direct dissemination of units and to coordination of national measurement standards. So this all is being taken care by BIPM. So they are the absolute authority. And so this is their headquarters in Paris. This is their logo, and this is their website. So bipm.org. You will get lots of resources on this website related to SI units and metrology and many other things. So if you feel really interested, I strongly encourage you to visit this website. Now, has the SI been same since its inception? No, it has been changing. And as I said, the key idea of SI is for all times, for all people. So that means that it has to be ensured that the measurements are being continuously improved. And as the science and technology is progressing, the definitions are also changed. For example, you can see how it has been changing. In 1960, the name adopted by 11 CGPM in 1960 for the system with 6 base units. That time only 6 base units were there: kilogram, second, meter, ampere, Kelvin, candela. In 1967, the second was redefined. I'll come later on in my slides how second has evolved, the unit of time. In 1972, mole was also introduced as a unit, as a base unit. In 1979, the candela was redefined. In 1983, meter was redefined and first time on the basis of a fundamental constant. In 1990s, other electronic techniques were introduced. The international temperature scale was adopted, and very recently in 2018, the 26th meeting of CGPM, they agreed to revise the SI on the basis of fundamental constants. Specifically, the 4 units, the 4 of the base units were changed together, and this results in a system of SI units where all the base units are now defined on the basis of fundamental constants, which many of you must have read in your science books. For students of class 6 to 8, probably they will read in 9th, 10th, but 9th onwards, and especially in 11th class NCERT textbook, there is good amount of information about SI units, and it also mentions about NPL, keeping the standards for the country. So why the evolution is done? As I said, there are certain prerequisites to redefine the units and to make changes into the SI. This can be like if there are some issues with the present definition, some things are being changing, the measurements are not still ideal, if there are non-uniformity and large inaccuracy in its realization, if there is some global SI inconsistency, like some other part, people say now we have better measure or better idea to measure a certain quantity, that calls for a redefinition. And then advancement in science and technology surpasses the present definition. So suddenly one group of scientists, they discover a better way of measuring certain quantity. So then they will expose it to others. The others will also try to realize, and once everybody agrees, then it makes a case for CGPM to consider a redefinition. So that's how the SI has been continuously evolving. So you can have your complete trust in the SI units. So this is the set of revised SI units since 2019. So this also came in force. It was accepted and agreed to in 2018, but it was implemented from the World Metrology Day in 2019. So 20 May 2019 was the day from when these units came into force. So now all the 7 base units are defined in terms of the fundamental constants. I think I don't need to read these all. You must be aware of it, or you can read about it. So the revised SI, so you can see these are the fundamental constant and the units. The second, it is related to the transition in cesium atom. Then ampere is related to elementary charge. Kelvin is related to Boltzmann constant. Mole to the Avogadro number. Candela to the candela, and then kilogram to Planck's constant, and then meter to the speed of light. And what also has been changed, so this was the order of the old SI. From the new SI, the order has also been changed. So how does it matter? It looks almost same, right? But the difference is the unit on top is a unit which is realized independently. It doesn't depend on other units. While kilogram, for its realization, it needs the traceability from second and also meter. Similarly, meter also needs second. So second sits on top because it's the only base unit which can be independently realized. It doesn't need help of other SI units. So this is the revised order also in place when the new SI system was adopted in 2019. So these are the defining constants and their corresponding value, the symbols, the base unit, their associated symbol, the names of the constants, and their symbols and values. They are all mentioned. So these are like by fixing, the units have now been defined by fixing the value of these fundamental constants. And of course, because these are SI units, so they all of them have zero uncertainty. So these are perfectly defined after various sets of measurements, and this is what everybody refers to. So this cannot have uncertainty. The other measurements which will follow from there, they will have uncertainty. So now let's go quickly to the SI units one by one. So the second, which is the SI unit of time, it is defined by taking the fixed numerical value of cesium frequency. So cesium atoms, they emit microwave radiation of this frequency, and so this microwave radiation is absorbed by atoms and they change their state. So by manipulating the cesium atoms and by measuring this transition frequency in cesium atoms, we can realize a clock. We can realize the interval of time, which is 1 second. So this is defined by taking this fixed value of the cesium transition frequency. So I'm related to the time and frequency standard, and I work with the realization of second in India, and I work on the atomic clocks, but that is not the topic I can discuss in detail in this talk. There will be some other talk where I can tell you about timekeeping with atomic clocks. So evolution of second, as I said, it has been constantly, refined, the measurement of second. So before 1960, it was taken as fraction of mean solar day. The earth is our reference and earth rotates around sun, so our one day is kind of fixed, but we know as scientists that the day's length is not fixed, it changes. And also the speed, the earth is rotating and that speed is also not constant, and that is why it was suggested to move to a definition which is not dependent on planetary objects. So then in 1960, the second was taken as fraction of some tropical year. So this was also some convention, which, I mean, it's really not very well understood why this was taken. This in 1967, it was finally decided to switch to the cesium atom based definition based on. So this was the first quantum definition of an SI unit. It is based on a quantum principle. Then in 1997, the definition was further revived. Only the temperature of atoms at 0K was added. So even to this level, you can imagine that the CIPM, PIPM, and CGPM, they work to make sure that there is no confusion. There should be an absolute integrity to every measurement. And for that, if it requires to add a certain sentence to the definition, because everybody all across the world will adopt these definitions, just by the words. So they were revised. And 2019, because cesium was already a good reference for SI second, only the phrase was changed. It was rephrased. So it's the same unit and the realized also in the same manner, but it's only rephrased. So what is a primary standard of time and frequency? I just told you that there are atomic clocks where we manipulate cesium atoms and measure the frequency. But the primary standard is called a cesium fountain frequency standard. So basically, time we measure indirectly, not directly measuring time, but we measure frequency first. And from there, by counting those frequency, we can get the interval of time, which is 1 second. So a cesium fountain clock, atoms are laser cooled and then exposed to the microwaves, because this transition, which we measure in cesium atom, is in the microwave domain, 9.19 gigahertz. So, and then they are probed for their state. So their transition probability is measured. And this kind of atomic clock, which is a cesium fountain atomic clock, they are very rare. Only 10 countries in the world could realize, and India is also proud to have developed at NPL. This is my primary work that I do of development of cesium atomic primary frequency standard for the nation. And it has a relative uncertainty of part in 10 to 15 or 16. So frequency is the most accurately measured quantity, the most out of all the SI units. So what about the SI unit of length? It's meter. So it is taken, it is defined by taking the fixed numerical value of speed of light in vacuum. But for the realization, it also depends on time. So basically, it also depends on the cesium frequency. So how it has been evolved? So since 1901, the international standard of length was a prototype, a bar of meter, and the meter was defined as the distance between two lines on a ruled on a platinum iridium bar. It was carefully preserved in a special vault in BIPM, because it will be used as a reference worldwide. So this bar has to be protected about any kind of degeneration. Then in 1960, the meter was redefined, and this was redefined on the basis of a wavelength now, because it's a more closer to it, I mean a more fundamental quantity. So then it was based on wavelength in krypton isotope. In 1983, the meter was redefined again. And to the definition which still holds today. The meter is the length of path traveled by light in vacuum during the interval of a second. So it depends on second. And it is realized using a iodine stabilized helium neon laser, specifically in India. So this is a primary standard. But these days, we can also measure. So the SI unit of length, meter, is realized indirectly. It's not a direct measurement. So we first measure the fixed frequency of a laser, and then we can employ interferometric methods to calibrate a artifact or the device under test to calibrate against this standard primary standard of the length. So so until the development of frequency comp in about 2000, then we used to do an interlaboratory comparison. Still we do. If we can't have a frequency comp, we can still do that. And the beat frequency measurement method is employed. So for historical reasons, 633 nanometer frequency was used in many NMIs, and even in India, we use the iodine stabilized helium neon lasers. But the BIPM has prescribed a set of frequencies which can be measured for the realization of 1 meter, and the uncertainty typically lies in the order of parting 10 to 11. So for the unit of mass is kilogram, and it is defined with fixing the value of Planck's constant. So now it is directly related to Planck's constant, and it is the biggest change, one of the biggest change in the new SI, which has come in place from 2019. So in 1791, kilogram originated from a physical constant, density of water. It was related. In 1795, it was amended, and the conditions were changed, the conditions of water. In 1799, the kilogram was changed again by adopting material artifact known as the kilogram of the archives, which was a cylinder of platinum. In 1889, the unit of kilogram was redefined on the mass of international prototype. So an international prototype was made. This was basically a cylinder of platinum iridium alloy. This was made, and it was the material properties are so that it will not degrade over a long time, but still it is preserved in vacuum jars. And the copies were also made, and these were dispatched to the signatories. So each member country received one copy of this cylinder. And in 2019, this artifacts based unit definition was changed, and now it is defined with the fundamental constant, that's Planck's constant. So the primary standard till the revision of SI in 2019 has been a prototype of kilogram, which looks like this. And international prototype of kilogram is kept at BIPM. It has been conserved, and the copies are there with other countries. For example, in India, we received a copy of it, which is called NPK. So the National Prototype of Kilogram, copy number 57. And it is secure at NPL with the director as the custodian of this. It's a very important thing. And it was provided by the BIPM. And since then, because it's a material-based, artifact-based standard, it is sent for recalibration every couple of years. And there is a set procedure of recalibration at BIPM. But at the moment, it still serves as primary standard in India. And the mass value from this is disseminated to NPL mass standards from 1 milligram to 2000 kilogram, and solid density standards in volume and others can also be measured. So this is what is NPL capable of providing calibration for in this range. But it is improving. So right now, this Kibble balance, so with the Planck's constant, what is the way to realize the kilogram? So this is done by, again, this is beyond the scope of this talk because it's already covering all the SI seconds, but it is done by, balancing the mechanical force with the electric force. So you keep the mass to be measured in one plank of the balance, and on the other one you have a magnetic coil and set of permanent magnets, and you flow the current to balance this. So you have this gravitational force pulling the mass down, and then you have the electric force which will push it up and balance the two. So once it reaches the equilibrium, then you measure the current, and from there you can deduce the mass via involving the Planck's constant. So that is how it is done. Many countries in the world have already done it, and India is also developing. So at NPL India, my colleagues are developing the Kibble balance for the country. So similarly, now I'll quickly go through other units of SI system, because these are just definitions and you can read about them. They are available on internet. So the ampere, this is defined with the electric, this is defined by the elementary charge of electron. So this is the definition. And it also needs, again, this is not independently measured. It also needs second for its realization. Then the unit of temperature, earlier it was triple point of water and other things, but now it is related to the Boltzmann constant. And Boltzmann constant relates the energy to the temperature of any material. So from there we can deduce the temperature if we know the Boltzmann constant, and the value of the Boltzmann constant has been fixed. The unit of amount of substance is mole, and this is this is done by measuring the elementary entities in 1 mole. So Avogadro constant is defines what are the number of entities in 1 mole. So this is defined with the Avogadro number. Another SI base unit is the luminous intensity, the candela. So the symbol is CD. So it is defined by taking fixed numerical value of luminous efficacy of monochromatic radiation of 540 terahertz. So, I mean, this must be confusing. So why 540 terahertz? So 540 terahertz is the green light. And this particular wavelength of green light is what our eyes are most sensitive to. So for 1 watt of power, how much green light of this wavelength is generated is what candela defines. So that is the luminous efficacy. So 683 units, luminous intensity per watt. So that is lumens per watt is what defines the candela. So these are the 7 base units I've taken you to. Then these are the base units, but we have many other measurements, right? We have magnetic flux, we have voltage, we have pressure, we have stress, we have density, we have volume. So how are they measured? So these are called derived quantities. So present SI system has 7 base units and 22 derived units. And these derived units, why they are called derived? Because they can be obtained from the base units by an algebraic equation, either by dividing or by multiplying. We can get to the other units. So that's why they are called derived units. So then also the SI defines about the multiples, because everything has to be uniform, not just the measurement, but also the representation of units have to be uniform. So this is how the multiples and submultiples are defined by giving the names to the prefixes. Like if the factor is 10 to 1, deca, hecto, kilo, mega goes up to queta if it is 10 to power 30. And similarly for the submultiples, going from deci, centi, milli to queto for 10 to minus 30. So some of you probably might have read about such high multiples or the submultiples for the first time, right? And then you can go to the BIPM website for the a guide for this is vocabulary in metrology. So there are many terms that we have touched: metrology, uncertainty, precision, accuracy, and so many more. You can read more about it by visiting the BIPM website and getting this vocabulary in metrology. So realization, how the SI units are realized. So for the practical realization, the consultative committees of the CIPM, they have defined the information booklet for practical realization. So that everybody gets to know how a certain unit has to be realized. So the realization of all 7 base units has been published on the BIPM website, and these are called Miss and Pratik. So Miss and Pratik is a guide to measurement, practical guide to measurement. This is a French acronym again. So to realize a unit means establishing the value and the associated uncertainty of the quantity. So these Miss and Pratik, again, they are available for each unit. I mean, we could discuss them one by one, but again, it's outside the scope of this lecture, because our younger audience, the students of class 6 to 8 may get really bored for this. So why SI? We have talked so much about SI. So SI is required for consistency, because we have a universal system of measurements. It's consistent with all industries and countries, so there's no confusion, no errors. Ease of communication. So what the scientists in India measure and communicate in terms of their papers, what are the findings here, they can communicate to outside India. And science and technology is done on a global level. It cannot be within the country. It has to be communicated. So if we have same system of measurement, the communication can be done very smoothly. Then for enhanced accuracy, especially in manufacturing, in industries, in healthcare, these accurate measurements, they are critical for patient safety, well-being. Then international acceptance, because it's a globally accepted system, it's easier for businesses to export their products, which is critical for quality control and international trade. So if you export an Audi or a BMW, which many people in India are doing, but you cannot repair it. So if a nut and bolt has to be replaced, when in India, if the measurements are different from that in Germany or US, how will you get your car repaired or fixed? So that's how, if there are systems in place of measurements, and you are measuring the same size for nut and bolt, which America also measures and tells in their brochure, so you replace this bolt of this much size, and you can find it locally because it's available. In India, people are also making the same measurement, then it's easy. So it helps the quality control, it helps the international trade. And then the quality. So adherence to SI improves the quality infrastructures, and it improves the quality of life of everyone. Just imagine, I mean, if you can be sure that the milk wala is giving you 1 liter of milk, and that is exactly one liter. The gas cylinder has exactly 14.6 kilogram. The vegetable vendor is giving you exactly 1 kilogram. If you don't have to worry about like being cheated, and if you can know, okay, I got my diagnostic test done, and my blood says my hemoglobin is low, so I should take some iron supplement. And I should be assured of that. It should not be like I got so the quality, you have peace of mind, and the overall quality improves, and that also improves the economic development. So all the industrialized nations, if you see, like you look at USA, UK, Germany, European countries, so you look at carefully, all of these countries, they have a highly developed metrology, and the temperament, the metrological and scientific temperament, it's not just restricted to the labs. It is percolating to the common man, to common people. So you, as the ambassadors of the new and upcoming India, if you people are aware, I think our job is done. If you can understand the importance of SI units and measurements, I think we have done our task. So it is a very important field of study, but unfortunately, it is not taught in detail in schools or college education. But I think we should talk more about it. And I think at the end of this lecture, you have realized why it is so important. So then, as we said, quality infrastructure. So what does quality infrastructure mean? So the quality infrastructure consists of many things. So for example, the institutions that are directly involved, like metrology, standardization, accreditation. So somebody will write the standards, somebody will measure, like we do metrology, we measure. Standardization comes from other institutions like BIS, Bureau of Indian Standards. The accreditation comes from NABL. So they accredit the labs if they are making correct measurements. Then there are infrastructure, quality infrastructure services. So calibration and testing services we provide, certification, inspection, conformity assessment. So these services have to be there. Then the S&T institutions, they have to provide accurate and precise measurements for new science and technology as well as new innovative products. And the customers should get, the enterprises have to ensure their product and process quality, which will help in international trade. The consumers will get satisfaction that they are getting quality products, clean environment, food and health safety, everything. So they will have a peace of mind, and the government will get, the suggestions for policies and regulations. So if it is realized there is too much adulteration in milk, and many labs in the country measure it, and then the government gets to know, there is something going wrong with the milk quality, so we have to make certain regulation for all to follow. So this is how the quality infrastructure in a country is developed. And so what is the role of the national and international institutes in assuring the quality infrastructure? So there are various aspects. So as we just said, metrology, accreditation, standards, certification and testing. So for metrology on national level, we have CSR NPL. So we are the National Metrology Institute of the country. And we also have a legal metrology department for enforcing that everybody does correct measurements. And on the international level, we have for metrology BIPM, an international organization of legal metrology. For accreditation in India, we have accreditation board for testing and calibration of laboratories, and similarly we have board for hospitals and various other sectors. Then for standards in India, we have BIS, and on the international level, we have International Organization for Standardization and in International Electrotechnical Commission. So they prescribe, they write the documents for standards. So NPL, as I said, is a National Metrology Institute by an Act of Parliament, and we deal with all 7 base units except for the ionization radiation, for which the Bhabha Atomic Research Center in India is the designated institute. And NPL is a member of BIPM, and it is signatory to the International Committee of Weights and Measures Mutual Recognition Agreement. So, which means we also have the internationally kept practice for following the SI traceability, and we provide the accurate measurements. So, the measurements done at NPL will be valid in other countries as well. And we are also founding members of Asia Pacific Metrology Program. So there, the whole world is divided in 6 regional metrology organizations. There's so much to measurements and metrology and SI than probably what you have read so far. So then this is the mutual recognition agreement result. So something measured at NMI1, so 1 kilogram at NMI1 will be 1 kilogram at NMI2. So measured at NPL India or measured at NIST in USA or NPL in UK. So every country has one NMI. So it will be accepted. So this is the degree of equivalence between the NMIs. So how NPL disseminates SI in India? By following this traceability pyramid. So what is this traceability pyramid? So on the top are SI units, and then we have primary standards or national standards. Then we have secondary standards, reference standards, working standards, and measuring instruments. And specifically in context of India, these are units, but BIPM or CIPM decides on units. NPL realizes primary standard because NMI hai accredited and government laboratories and sectors are there for providing calibration services, and then the manufacturer and end user gets the traceability. So one side, the traceability. So we are providing measurements to the SI, traceable to the SI unit, and then we are providing calibration down to the end user level. So this is the traceability pyramid, and the main idea is the unbroken chain of measurements for quality, so that the manufacturers and end users all are assured about quality. So why is SI traceability important? To make accurate measurements, to make science more scientific, technology more perfect, because if you are making the correct measurements and each instrument that you are developing or each technology gives you the same result, that is where the metrology helps you achieve that. Environment will be cleaner, energy sustainable, healthcare will be affordable and more trusted. Strong cyber security, barrierless international trade, and we can also suggest a nation building policies. So this is how the SI helps in the inclusive growth of the nation, and ultimately the economic development comes from these practices. So if you're bored and lost in SI and metrology, because I've been speaking for about good 1 hour, and then especially for our younger audiences, so the NIST, which is NMI of USA, they have made very nice superheroes, the SI superheroes. So you see all 7 SI units, and also for the uncertainty, there is a unit and a cartoon, and they have also made series of SI superhero videos. So if you, and I know the younger generation these days doesn't have a large attention span, and the attention runs out quickly, and you learn more by visually seeing something. So you can visit the website and look at these videos, and you will never forget about the SI base units. And if time permits, Richa, may I show one video? I hope it works. If it doesn't, I will have, oh, it's somehow not working. I could have played it, but I think it's not working. Nevertheless, I think you can visit this website, this link, just note it down, and you can visit some videos about how all measurement aspects are critical. So with this, I would like to thank you all. So the take-home message is NPL is the National Metrology Institute of India. SI units and metrology is essential for each and every sector, and for quality infrastructure, for quality of life, and for economic development. And this is the traceability pyramid, which is essential for ensuring quality. We have at NPL SI unit of measurement wall. So I know that CAMP also facilitates lab visits. So I would really encourage the school students to visit NPL. Every year, end of September, we have open day where our laboratories are open, to students. And the idea is again outreach and developing scientific temperament. So you are most welcome to visit and see these art, monuments, so to say, at NPL. And just remember, NPL takes care of all the measurements, and we are also the timekeeper of the nation. And we maintain and measure the Indian Standard Time with nanosecond accuracy. And we also provide traceability to ISRO for its satellite missions and so on. So these are the take-home messages, and I thank you all for your attention. I think it was one good hour of the lecture. I hope you could gain some knowledge from it, and I think I should stop here and take up any questions that you all might be having. So thank you so much.
All right, ma'am. Thank you so much. This was a lovely session. And somebody like me coming from the humanities background is, definitely, I feel that, these things are so basic and something that, we use in our everyday lives. And
Yes,
somehow we
absolutely.
kind of don't notice that these,
Yes.
things like these are so important, especially the measurement, as you
Yeah.
mentioned, is it is so useful in healthcare and other thematic
Yeah.
areas. So,
So from now on, if you visit, a lab or a vendor or something, you will ask, "Are your instruments calibrated?"
right.
Yeah. Yeah.
So, okay, ma'am, I wanted to ask you a few questions. My
Mhm.
question starts with the IWSA.
Yeah.
Right? That is
Right.
the, yes. So could you please highlight if what is the eligibility like? And because as you mentioned that you don't have to be, you don't have to be a woman in necessary. You can be a male
Yeah.
aspirant
Yeah.
if you join this association.
Yeah. So this association, you will get, as I said, all the details are available on the website. So anybody, any woman having a background in science and technology can easily become a member. There is a membership fee for that, and there is also provision for associate membership. And also, like some learned male colleagues, if there are like some teachers or some speakers, we call them friends of IFSA. So they can also, take part in our activities. If somebody has an idea for a lecture or a project or a workshop, so these are basically for community. I mean, we are doing it for community's sake. And for example, when we have the lectures or nurture program, we don't see that they're only girls. I mean, they can be boys too. So these are not restricted only to women.
Hmm.
So it's just a women body, so the membership largely is women. All the members are women. But as I said, friends of IFSA is one possibility, and then students can visit the website. From time to time there are announcements about lectures, about projects, about nurture program, and all the branches of IFSA. Like I am associated with Delhi branch, so we keep conducting sessions and lectures and activities, sometimes even industry visit or something like that. So those outreach events is also one of the activity of IFSA.
Right, ma'am. So, students, the floor is open for every one of you to please ask Dr. Poonam Arora the question regarding the session. Can we please take up the question now?
So no one asking. Are they able to unmute themselves? Is there an option, or they can write on the chat?
Then they can write on the chat and we'll unmute them.
Hello, ma'am.
Yeah. Yes.
Hello,
Ma'am,
Drishti.
ma'am, listen all the things. Your speaking thing is very good about this workshop and all these things. So,
Mm-hmm.
ma'am, can you tell where we can search of this video and all things?
That video I told you is available on NIST, and I had already
And
shared
I
the
speak.
link. I'll flash that link again. And
Okay.
along my slides, I had been telling about some of the references which
Okay.
you can look into. But the
Yes, ma'am.
bipm.org, so this, like, bipm.org is one where you can get all kind of information or links, to various things. So I encourage you to visit bipm.org, and for the videos, especially those superhero series, I am sure many students are interested. You can visit nist.gov/education, and you'll find these. And or you can just Google SI superhero videos. I think Google will also take you to this NIST link. All right. Do read about these things and get yourself acquainted with all these concepts. Anything else? Somebody else has also raised hand. Navya. Navya, go ahead. Ask your question. It's always good to ask questions.
Actually, I was saying for this slide only, so now it is there, so I was writing the link.
All right, all right. Otherwise, I will send this link also to the camp people, and they can share it with all of you. I mean, I'm sure you will be interested. Even as a grown up, even I was interested, and I had fun watching these videos. So I'm sure at least all of you will understand and have fun, learning SI in a more lucid manner. Anything else?
Okay,
Any other question? Kids, you can come up. No questions are stupid. There are only stupid answers. Questions are always good. Any kind of question. Yeah, Drishti, go ahead.
Yes, ma'am. So, ma'am, your session is very good about regarding me. I'm not like in when I am in the school, so I'm not interested to attend this all the things, and always say to my teacher that, ma'am, please give us to write the work and all. So I now I am understand the why is workshop is necessary to attend.
Yeah, good. I mean, you get to know about something outside your textbooks. I think it's always important, and when
Yes,
you
ma'am.
get this in a capsule manner, concentrated information on one subject, I hope it helps. So I'm really happy that you are appreciating it, and I wish you good luck for all your endeavors.
Yeah. Thank you, ma'am.
Yeah, Tanush.
Yes, ma'am, first of all, thank you for this lovely session, and I love this lecture. And I want to ask you a thing like, what will happen in this say superheroes measurement league? Like, what?
What will happen? Okay, so just for you people, or for just for anybody, to make it understandable, they decided, because kids like watching cartoons, right? You must be watching some cartoons. You must be aware about Doraemon, or Tom and Jerry, and so on, or Pokemon. These days people watch. So similarly, the way you remember those cartoons, I mean, if the science is also made interesting, so this is an attempt so that children can understand. So after looking at these posters and some videos on the SI, one thing you will realize the importance of measurement. Second thing, you will realize these characters will be imprinted in your mind. You will not have to really work hard to remember that SI unit of time is second. You will remember, oh, Professor Second, yeah, and Meter Man. All right. So what does Meter Man do, and what does Professor Second do? When you watch these videos, you will get to know. So you will understand, and it will help in retention, better retention. It has been proven that visual, when you see something visually, your retention is better. So good luck. Enjoy these videos. Yes, Divya. Divya, go ahead, unmute. Is she not able to unmute herself? Tanush, you have anything more to ask? Probably not.
Okay, we have Drishti who wants to ask something. I'll just unmute her.
Sure.
Hi, ma'am.
Hello? Yes? Ask your
Ma'am,
question.
ma'am, I need.
If there is issue in bandwidth, you may write your question in the chat box and probably we can read, or maybe Richa can read it for me. I think there are some questions in chat.
All right, students, I believe we have some technical issue and we're running short of time also. So we